I want to talk today about enolate chemistry, and I want to start by talking about the equilibrium between two different forms of a ketone. The keto form, where I have a C double bond O, and the enol form, where I have an OH and a C double bond C. It's called the keto-enol tautomerization. Tautomerization is just a fancy name for this equilibrium. This is the keto form, this is the enol form, and it's the enol type form of the compound that we're going to be interested in looking at and using for our reactions and our reactivity. Unfortunately for us, this equilibrium gives us very, very little of the enol form. It's almost entirely the keto form. These numbers are only approximate. It depends on the exact nature of the ketone and so on. But approximately 99.99% of the compound is in the keto form, and only 0.0001% is in the enol form. That's nowhere near enough for us to do anything interesting in terms of chemistry with. What we're going to have to do is we're going to have to look at a related compound, something similar to the enol, something called the enolate. When we look at the enolate, we take our ketone, or we could do this with an aldehyde also, and we treat it with a base. We treat it with a base because these alpha hydrogens are somewhat acidic. They're not incredibly acidic, they're somewhat acidic. If we look at the pKa's for various carbonyl derivatives, the aldehyde will have a pK of about 17 for those hydrogens. We call these the alpha hydrogens because they're on the alpha carbon. For the ketone, it'll be about 19. So like I said, they're somewhat acidic. And if we treat it with a strong enough base, which we'll talk about in a little bit, we can get removal of that hydrogen. And what we get is this product where we have a negative charge right next to the carbonyl. There's a lone pair of electrons there because we removed the hydrogen, left the electrons in the bond behind. We can actually draw a resonance for this, where these electrons move in. These move up onto the oxygen, and when we do that, what we get is this resonance structure right here where we have the negative charge on the oxygen. And you can see there's a similarity between the enol structure that we drew here and this compound right here, which is the enolate. It has a negative charge on the oxygen. It's the enolate. And of course, because these are resonance structures, we want to put the brackets around them to indicate that they are. So let's talk about making the enolate of cyclohexanone using a base like Tbutoxide. Now, Tbutoxide is strong enough to give us some enolate, but not 100% conversion. You'll see that this is our enolate product, and depending on the strength of the base and the particular ketone you're looking at, you will get approximately 1% of your enolate product and 99% of the starting ketone. Now this negative charge right here, this negatively charged carbon, it can act as a nucleophile. And it can do an SN2 type reaction if you treat it with something that has a good leaving group like methyl iodide. And you'll notice that this second product, the reaction to form it is not reversible. And this kind of shifts the equilibrium in the direction that we want it to go. This particular product, this is called an alkylation reaction. This is the alkylation product. We did the alkylation of an enolate. Now things are a little bit different for this cyclohexanone derivative because I've got a methyl group on one side. This is actually not symmetric. If I generate the enolate on one side, it's going to be a different enolate than if I generate the enolate on the other side. So if I remove this hydrogen, I end up getting this enolate. If I remove either of these two hydrogens, I get the other enolate. Now, we need to talk a little bit about the nature of these two enolates. In particular, I want you to notice that because of this methyl group right here, this hydrogen is a little bit more sterically crowded, and these two hydrogens, there's nothing blocking them. They're a little bit easier to get to. They're less sterically crowded. Since they're less crowded, less sterically hindered, they're removed faster. You'll remember from earlier this semester, the product that forms faster is called the kinetic product. So this is the kinetic product. On the other hand, if we look at this product, this double bond is more substituted than this one. Since it's the more substituted double bond, this is the more stable product. Again, you'll remember from earlier this semester, we called the more substituted product the more stable product, the thermodynamic product. So we have the thermodynamically formed product. The thermodynamic enolate has the more stable product. The kinetically favored product, the kinetic enolate, has the faster, rapidly formed product. So how do we get each of these? Well, the kinetic product is formed fast and is irreversible, so there'd be conditions that don't allow equilibrium. So strong base, low temperature, no equilibration. On the other hand, for the thermodynamic product, we want it to equilibrate. So we want slightly higher temperatures. We want a base that's about the same strength as our ketone or our aldehyde, so it equilibrates back and forth. So a weaker base and a higher temperature give us equilibration to make the thermodynamic product. Now it's really important that we notice the terms here. I'm not saying a weak base, I'm saying a weaker base than for the kinetic product. I'm not saying high temperature, I'm saying higher temperature than the low temperature we have for the kinetic product. Now let's look at some examples of this. So if I take Tbutoxide 0 degrees Celsius with this alkylating agent, it has a leaving group, the iodine, these are conditions that will give me equilibrium. This Tbutoxide and the ketone are similar in base strength. So when I mix this together, what I'm going to get a mixture of this product, the product where my substitution happened at the least substituted enolate, the least substituted alpha carbon, my kinetic product, the major one under these conditions, and my thermodynamic product, where substitution happened at the more substituted carbon, my minor product under these conditions. On the other hand, if I use LDA, which is a really strong base, it won't give me any equilibrium at all. I use low temperature to further reduce the chances of getting equilibration. I'm going to get mostly my thermodynamic product substituted at the most substituted alpha carbon, and my kinetic product substituted at the least substituted alpha carbon is going to be my minor product. So this is a way that you can get one product over the other. However, I want to point out to you that it's very common to use LDA whether you want the kinetic product or the thermodynamic product, but by modifying the conditions a little bit, we can use LDA to get either our kinetic enolate or our thermodynamic enolate, and I want to show you those conditions now. So my kinetic conditions, I use the low temperature, I use extra LDA, just a little bit more LDA than my ketone. So if 1 mole of this, I have 1.1 moles of LDA. And low temperature, as I said, I will get mostly my kinetic product, 72% to 28%. On the other hand, using slightly higher temperatures and using less than a full equivalent of LDA allows the reaction to equilibrate. And when it equilibrates, I can use LDA to get a majority of my more substituted, more stable product. So we can really use LDA to either our kinetic product or our thermodynamic product, depending on the conditions we use. So applying this to our previous example, if I take this ketone and I want to substitute my ethyl group at my least substituted alpha carbon, I want to do this under kinetic conditions, low temperature, excess LDA. When I do that, I'm going to get primarily my least substituted kinetic product. On the other hand, if I have the temperature slightly higher, well, minus 78 is really cold. 0 degrees is still cold, but it's higher than minus 78, and not a full equivalent of LDA, a little less LDA than I have ketone. Under those conditions, instead of getting substituted at the less substituted carbon, I'm going to get reaction at the more substituted carbon. I'm going to get my thermodynamic product. So we can use LDA to get either our kinetic product or our thermodynamic product.